welcome to the MAML Manual. I'm Iris.
And I'm Sebastian.
And today we'll be covering meet number 1, topic number 5, geometric similarities. Let's jump right into it. Alright, here's our first problem for geometric similarities. Just 2 quick reminders. 1, the problem and year will always be posted in the corner down here if you're following along in your packet. And also, this is a calculator section of the meet. The last section of every meet is going to be calculators allowed. And I'll get into rounding details later if it comes up. Alright, so let's jump into it. Given triangle ABC is similar to triangle DEF with side lengths as given, find the length of side DE. Express your answer in feet and inches. Alright, so the first thing that I noticed is that these triangles are similar. So just to help my brain understand how this is working, I'm going to orient them positionally the same. So we have triangle, let's see, ABC here, and this leg is 130 inches, and this leg is 65 inches. Okay, now triangle DEF. And this leg is 104 inches. So we're trying to solve for this side length. So I'm going to assign this side length a variable. Let's just say x. Since these are similar triangles, we can set up a relationship between the two and solve for x. So we know that 65 is to 130. So I'll write that over here. 65 is to 130 as, so it's going to be equals, x is to 104. Because proportionally, the side lengths are going to be the same on each triangle. So all we need to do from here is cross multiply and solve for x. So we have 130x is equal to 65 times 104, which is 6,760. Divide both sides by 130. So we have x is equal to 52. So that's our answer in inches. But notice, the problem is asking for our answer in feet and inches. So we just need to turn 52 inches into feet and inches. And we know that 48 inches is 4 feet. So we have 4 feet and 4 leftover inches. And that is our answer. Let's move on. Here's our next problem. Find x and y for the segments AB, BC, PQ, and QR in the following diagram. The horizontal lines are parallel. Alright, so they give us the diagram, and we know that these horizontal lines are parallel. Also, this transversal right here, we know that these two segments are both equal, meaning that these parallel lines are equidistant apart. So we can set these equal to each other. Also, the same applies for this transversal. We can set these two segments equal to each other. So then we just get solving for each individual variable. So if we set these two equal to each other, it's going to be 2x plus 3 equals 6 minus x. Alright, so I'm going to subtract 2x on both sides. 3 equals 6 minus 3x. Subtract 6 on both sides. I'll bring this over here. Negative 3 is equal to negative 3 times x. So we just divide both sides by negative 3. And we get that x is equal to 1. That was pretty simple. And all we have to do is do the same thing on the other side with y. On this side, 4/3 y plus 1 is equal to 2y. So I'm going to subtract 4/3 y from both sides. So we're left with 1 is equal to 2/3 y. multiply both sides by the reciprocal, 3/2. We have y is equal to 3/2. And it's just asking for x and y. So our answer is going to be x is equal to 1 and y is equal to 3/2. Great, and that's our answer. Okay, here's our next problem. In the diagram, segment BC is parallel to segment ED. Segment AB equals 5. Segment BC equals 12, and BE equals x. And DE equals 3x plus 1. Find the length of segment AE. So I'm just going to draw a little line over here, just demonstrating that this is what we're trying to find. Since BC is parallel to ED, we know that ABC and AED are going to be similar triangles. We know that because they share one angle, angle A, and also, since these lines are parallel, this AE is one continuous line. We know that these angles are going to equal each other. So angle B is equal to angle E, and same goes for this side. Angle C is equal to angle D. All right, now that we know that, we can form a relationship between the two triangles. So this side length 5 is to 12 as 5 plus x, not just x, we have to include this entire side length. So as 5 plus x is to, and then this side down here, 3x plus 1. Again, we're just going to cross multiply and solve for x. So we have 60 plus 12x is equal to 15x plus 5. Subtract 5 from both sides. So 55 plus 12x equals 15x. I'm going to bring this back up here. And I'm going to subtract 12x from both sides. So we have 55 is equal to 3x. Divide both sides by 3. We have x is equal to 55 over 3. But that's not where we stop. We are solving for AE, which is not just x. It's equal to 5 plus x. So I'm going to write that over here. AE equal to 5 plus x. So that's going to be 5, but I'll find a common denominator because we have 55 over 3. So 15 over 3 plus 55 over 3, which equals 70 over 3. You can leave your answer as an improper fraction. You can answer with a mixed number or a decimal. And like I mentioned earlier, since this is a calculator section, rounding is a little bit funky. Sometimes they'll specify a problem. Just follow that. Also, if you're at a meet, you'll hear an announcement and they will say round to the 10,000ths place, so the nearest 4 decimals. So I'm going to divide this and I'm just going to get a decimal answer. So 70 divided by 3 is equal to 23.33333, repeating. So I'm going to round out to 4 decimals. So it's going to be 23.3333. And either one of those work for your answer. All right, here is our first 4-pointer of the video. In the figure, PQ is perpendicular to QR. ST is perpendicular to QR. Angle P is equal to angle R. PQ is equal to 15. QT is equal to 24. And ST is equal to 8. Find the perimeter of the quadrilateral PQRS. So that was a lot of information. First, I'm going to start by putting in what we know. So we know that PQ is perpendicular to QR. So we know that this is a right angle. ST is also perpendicular to QR. So we know that this a right angle, and I'm just going to put it on both sides. Angle P is equal to angle R. So this and that. PQ is equal to 15. QT is equal to 24. And ST is equal to 8. Okay, so our goal is to find the perimeter of this one large quadrilateral. So we have one side length, we have part of another side length, but we're still missing two. So the first piece of information that stuck out to me was that angle P is equal to angle R. That seems like, I don't know, maybe a random detail, but that's going to help us and figure out both of those side lengths. So, what I'm going to do is I'm going to draw a line from S over to a point on line PQ. And I'm going to label that point, I'll label it U. So we just created a triangle here. And since this line is, since QR is perpendicular to ST, and I made a line from the top of ST over to PQ, I'm going to say that this line is parallel to QR. So I know that this is a right angle. Because if these two are perpendicular, and these two are parallel, this means these two lines are also going to be perpendicular. So looking at this, well, this means that these triangles are similar because they have three shared angles. One, angle R and angle P, plus they're both right triangles, meaning that this last angle is going to have to be the same because the sum of all the interior angles of any triangle is going to be 180. So I'm just going to draw that over here. This angle is going to be equal to this angle. So now, we could form a relationship between these, but first I'm going to fill in some more side lengths. Because we know that Q to T is 24, and U to S is the same length, I'm going to write 24 over here, because we know that this leg of this triangle is going to be 24. Also, we know that from T to S, coming along here, also from Q to U is going to be 8. And if this entire side length is 15, 15 minus this 8 is going to leave us with another leg of 7. So you could use the Pythagorean theorem to find out the hypotenuse of this triangle, but I know that one of the Pythagorean triples, one of the primitive Pythagorean triples is 7, 24, 25. If you didn't know that, that's completely fine, but learning some of those primitive Pythagorean triples are going to help you with time and efficiency in the meets. So I know that this side length is 25. So since these triangles are similar, we can form a relationship between the two to find the hypotenuse of RST and also this shorter leg. So I am going to say that since this is the only side length that both triangles have values for, I'm going to say that 24 is to 25. 24 is to 25, as 8 is to this hypotenuse, and I'm going to call that x. Is to x. So cross multiply and solve for x. So 8 times 25 is going to be 200 equals 24x. Divide both sides. 24. So x is going to be equal to 8 and 1/3. All right, so I am going to do the same thing to find this shorter leg. So we know that 7 is to 24. As this leg, y, is to 8. Again, cross multiply. multiply, so 24y equals 56. Divide both sides by 24. And 56 divided by 24 is y is going to equal 2 1/3. So I'm going to write those in 8 1/3, 2 1/3. So now we have all of the lengths that we need to find the perimeter of PQRS. So it's going to be this length, 25, plus this length, which is 15, plus this entire bottom length, which is not just 24, it's not just 2 1/3, it's going to be 26 1/3. 26 1/3, plus this length, which is 8 1/3. 25 plus 15 is 40, plus 26 is 66, plus 8 is going to be 74, so we get 74 2/3. And again, you could write that as an improper fraction, a mixed number, or as a decimal, but there you have our answer. All right, here's our second 4-pointer of the video. The areas of two similar triangles are 96 and 6, respectively. If the perimeter of the large triangle is 48, what is the perimeter of the smaller triangle? Okay, so I'm going to start by drawing our triangles. So let's just say this is triangle A. It's our larger triangle. And its area is 96. Unit squared. We don't have a unit. When you're answering anything, they're not gonna require a unit. But sometimes it is helpful to just keep track of what you're doing. But I don't think we need that for this problem. So that's triangle A, and we have triangle B with an area of 6. We know that the perimeter of this triangle is 48, and we want to know what the perimeter of triangle B is. Since we know the areas of both triangle A and B, we can find the scale factor. So to find our scale factor, I'm going to divide 96 by 6, because that's whatever you have to multiply 6 to get to scale up to triangle A. So 96 divided by 6 is equal to 16. So that's our scale factor between the two areas. But our scale factor between side lengths is not going to be 16. So if you have a scale factor of 2 between two triangles, generally that's referring to side length. To find the scale factor for the area, you square the scale factor between the sides. So we have the scale factor for the area, so I'm going to find the square root of 16, which is equal to 4. So we know that the scale factor between the side lengths of from triangle B to triangle A is going to be 4. Since we have the perimeter of triangle A, all we have to do is divide 48 by 4 to get the perimeter of triangle B. And 48 divided by 4 is 12. So the perimeter of triangle B is 12. And there you have it. Okay, here's our last 4-pointer of the video. Inside a regular hexagon, all 9 diagonals are drawn. This creates 24 polygons, none of which is crossed by a diagonal line. How many distinct polygons are there among these 24 polygons? Consider 2 polygons distinct if they are not congruent. Okay, so this one, considering it's a 4-pointer, is actually a surprisingly easy problem. So I'm going to start by drawing the diagonals in this hexagon. So if you didn't know, a diagonal is a line within a polygon that connects every single vertex to all of the other vertices besides the ones that are adjacent to it. So for example, we go from this vertex, I'm going to draw a line down here, here, and there. But not to these two, because those are adjacent and it would just be a line on the outside of the polygon. So I'm going to continue this going around. So here, 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 and then since this one already has one diagonal next to the point, or we just have to draw two more. And this one, there's already two drawn, so we have one more, and we get the last two, and all those are drawn. Okay, so now that we have the diagonals drawn, it's asking how many distinct polygons are there among these 24 polygons within the hexagon. So since I didn't use a straight edge, these are not going to be very accurately drawn shapes. Like for example, this little triangle here would not be there. They are all going to intersect right at the middle. So I'm just going to color that in to show that that is not a shape in our as we're counting how many there are. So let's start on the outside. Using the edge, I can see there's a very flat isosceles triangle on every one of the sides. So I'm going to mark all of those off and count them as one. Next, we can move inward. There are pairs of right triangles with the tip at every vertex. So there's going to be 12 of those all the way around, and we can only count one of these as one. Even though they may be flipped or oriented differently, they are all the same shape because they're all congruent. So I'm going to draw another one over here. And then finally, we get to these, well, if I had drawn the diagonals perfectly, they would all be quadrilaterals in the middle. And there's 6 of them, and so we can only count those as one. And that is our last shape. So, total, there are 3 distinct polygons drawn by the diagonals inside this hexagon. Alright, here's our first 5-pointer of the video. The 3 squares have the indicated lengths in the diagram. What is the area of the shaded quadrilateral? Indicated right here. Alright, so we have 3 squares here, meaning, as you know, all of the sides are going to be equal. So this is going to be 5, 5, 5, and so on. We can start by writing that the base of all of these squares put together, or the base of this triangle, is going to be 10. So we have 5 plus 3 plus 2. So I'm going to write 10 down there. Okay, so we're looking for this shaded region. And yes, it would be easy to say, okay, let's just find the area of this smaller triangle and subtract the area of the smallest triangle from the area of the smaller triangle. Well, we can do that, but we have to get there first, using our known lengths. So, this larger triangle has a base of 10 and a height of 5. The second largest triangle, we know, has a base of 5. So, if the base is half of this larger base, we know that the height is going to be half of the largest triangle's height. So we know that the height of this is 2.5. Okay, and we can apply that same principle to find the lengths of the smaller triangle. Before I go any further, I just want to note that there are 2 ways to solve it from this point. One, I'll show you the first way, which is the way that I solved it originally. And then there is another way. It may be a few seconds faster depending on your comfort level with the concept. So, I'm going to find the area of this triangle and subtract the area of the smallest triangle. So we know that the base of this triangle is 2, which is 2/5 of the base of this larger triangle. So we need to find 2/5 of 2.5 to find the height, and 2/5 of 2.5 is 1. Okay, so we can find the area of this larger triangle and then subtract the area of the smaller triangle. We know that the area of the smaller triangle is going to be base times height divided by 2. So 2 times 1 divided by 2 is just 1. So now to find the area of this slightly larger triangle, 5 times 2.5, which is 12.5, divided by 2 is 6.25. Now, all we have to do from here is subtract the small area, the unshaded region, from the larger region to find the area of just the gray region. So we have 6.25 minus 1, 5.25. So there we have our answer. So now I'm going to explain a different approach you could have had to it. As you may notice, this gray region is a trapezoid. And so instead of finding the area of this triangle, which was simple to find, we could just go based off this side length, this side length, and the height of our trapezoid. So I'm just going to write out the formula for the area of a trapezoid. It is A plus B divided by 2 times the height. And so in this situation, I'm going to draw it out over here. A and B are the sides that are parallel, and our height is just the height of the trapezoid. So we come back over here, seeing that the gray region is a trapezoid, and we find our two parallel sides, which is going to be A and B, 1 and 2.5. So 1 plus 2.5 divided by 2 times our height, which in this case it would be rotated, so our height would be 3. So times 3 equals, so 1 plus 2.5 is 3.5 divided by 2, 1.75, and then times 3, that also gets us 5.25. So both of these methods work. They both give us an answer of 5.25. All right, let's move on. All right, here's our next problem. In right triangle ABC, the altitude to the hypotenuse AB is drawn intersecting the hypotenuse at point E. If BC is equal to 3 square root 5 and BE is equal to 5, find the length of the segment AC. All right, so first, I'm just going to draw our triangle. So it's a right triangle. I'm going to orient it this way, and you'll see why in a moment. So this is our right angle up there, and it said AB is our hypotenuse, so A, B, C. Right. BC is equal to 3 times the square root of 5, and BE, which is the intersection of the altitude, is equal to 5. So let me explain what an altitude of a triangle is first. So when you have a right triangle, it is a line that goes from your right angle to your hypotenuse, and it is perpendicular to your hypotenuse. Also, it forms two similar triangles to each other and to your original triangle ABC, which is very interesting, and it's going to be very helpful for us in this problem. All right, I'm just going to also mark that this is the thing that we're trying to find, segment AC. Since we know that these two smaller triangles are similar to each other and the larger triangle, I'm going to draw them separately down here, oriented so that they are positionally the same as each other and as this big one. So we have E, B, C, and E, C, A. All right, so now I'm going to put our values in for our side lengths down here. So we know CB is equal to 3 square root of 5, and EB is equal to 5. And so looking at this, well, I see that CE is a shared side length of both of these triangles. So let's solve for that. We can just use the Pythagorean theorem to solve for EC. So we can say that our side length EC is going to be equal to the square root of 3 square roots of 5 squared minus 5 squared, which is, we do that out, 3 times the square root of 5 squared is equal to 45, minus 5 squared, which you know is 25, so square root of 45 minus 25. So EC AC is equal to square root of 20, or it's also 2 square roots of 5. So I'm going to write that over here, 2 square roots of 5. And since this is a shared side length, I'm going to write it over here, 2 square roots of 5. So now that we have one side length of this triangle, we can form a relationship between the two to solve for the side length AC, which I'm going to label x. So we know that 5 is to 3 times the square root of 5. 3 square roots of 5 as 2 times the square root of 5 is to x. So now that we have this, all we have to do is cross multiply and solve for x. So 2 times the square root of 5, 2 square roots of 5 times 3 square roots of 5 is going to be 6 times 5, which is 30. So it's equal to 5x. 30 over 5x, divide both sides by 5. We have x is equal to 6. So we know that the side length AC is equal to 6. All right, let's move on to the last problem. All right, moving on to the last problem of the video. To be completely honest with you, I did not get this problem on my own. It's not the most intuitive problem, at least in my opinion. So, 2 trees of heights 20 meters and 30 meters have ropes running from the top of one to the bottom of the other. How high above the ground do the ropes intersect? Assume the ropes have no sag. So, I'm just going to start by drawing this out. Sometimes it's easier to be able to visualize things. Okay, so we have one tree, so this one is 20 meters, and we have our other tree, 30 meters. And they have ropes going from the bottom of one to the top of the other. How high above the ground do they intersect? So this is the length that we're going to try and find. First, I'm just going to label all of our vertices. So A, B, C, D, and E, and F. Okay, so one thing to notice is that if you draw the ground down here, there's a smaller triangle, BEF, that's going to be similar to triangle BCD. Same goes for the other side. DEF is going to be similar to DBA. All right, so using these labeled vertices, I'm just going to start by writing a few relationships between these lengths. So we have BD is to 20 over here. D is to 20, as DE is to EF. So write that. DE is to EF. Because it's the length of this leg and the height. The length of this leg and the height. Alright, so let's do that with the other two similar triangles. So we have BD is to 30. As BE is to EF. BE is to EF. All right, so if you notice, we have these two fractions are very similar. They have the same numerator and they have a numerical denominator, so that's going to be helpful. These two fractions have the same denominator. So if you add BD over 20 to BD over 30, you're going to get BE over F plus DE over EF. And we know this because if these are equal, and and we add them to two values that are also equal, they're still going to be the same. So we can combine these because they have a common denominator, EF, and we can make a common denominator between these two. So I'm going to say 30 BD is over 600 plus 20 BD over 600 equal to BE plus DE over EF. So combine these, 50 BD over 600 is equal to BE plus DE over EF. All right, so if you notice, BE plus ED is just going to be BD. So I'm going to write that over here. I'm going to bring this up here. So we still have 50 BD over 600 is equal to BD. Like we said, we can substitute BE plus DE for BD because those are equal over EF. So now, if you notice, if we solve for 1 BD on the top of this fraction, then we are going to have the value of EF, which is the height above the ground where the ropes intersect. So we can simplify this to BD over 12 equal to BD over EF. And we know that 12 and EF have to be the same because they are being divided by the same value on the top. So we know that EF is equal to 12, meaning that these ropes intersect 12 meters above the ground. And there you have it. There's our final answer. All right, that's it for our video on geometric similarities.
Thank you for watching.
I'm Iris.
And I'm Sebastian.
And we're the MAML Manual.